So today we're going to work out example 562 in page 56 and till the end of that section. So we'll have a chance to actually do the maths on a kind of complete example. So I'll do that on the board, and hopefully that will help you to understand what's going on. And please ask questions if anything isn't clear. But before going into that, you probably know that next week is reading week. Nanjing students probably don't know exactly what that means, but there are no lectures in reading week. So we won't have lectures next week. But on week 8, 9, and 10, we have practical sessions, okay? Practical sessions are about using basically Markov chain Monte Carlo for Bayesian inference. And that's one of the main tools for doing Bayesian analysis, Bayesian inference in practice. So far, we haven't motivated, and we will not do that before the first practical session. We haven't motivated the use of these numerical techniques, so it will be a bit awkward. But hopefully, we will catch up in the lectures in that week, and everything will become a bit more clear. Okay, but what I wanted to draw your attention to is in the web page down there. Probably I can make it a bit bigger. That will make it. Hopefully you can read that. If not, it's in the web page. So we have practicals. There will be on Tuesday of weeks 8, 9, and 10, and there are 3 slots. One at 9, at 11, and at 12. All of them are in the Diamond, new building down the road. And the first one is in computer room 3. The other 2 are in computer room 2. Okay? So I've split the groups roughly in thirds according to your registration number. So the split is there. If anyone cannot attend a specific slot, just let me know so I can just keep tabs on numbers, right? We don't want people being without computers, basically, okay? So have a look at that, and if you have a problem with your assigned time, let me know as soon as possible, okay? Is that clear for everyone? Yeah? Cool. All right. Well, now that I'm there, the overheads that I will use for the practicals are also there, so you can download them. And the code that we will use in the first practical is that one. You can see the first example in chapter 7. And we will just finish chapter 5 today. So that's the kind of misalignment that we have. But we will catch up more or less quickly. Okay? Any questions so far? Okay. So yesterday, we stopped there. We had this example on pollution data where we had Gaussian data with a known mean and known precision. We had a Gaussian prior. We've worked out that the posterior will be Gaussian with a mean that is a weighted average of the MLE and the prior mean. And the weights will be proportional to the relative precisions of the likelihood and the prior. And once we have the posterior, any inference that we want to make will come from this posterior distribution, right? So in this particular case, given that the Gaussian, the posterior distribution is symmetric, the mean, the mode, and the median are the same. So we don't have a problem with that. We can quote the mean directly. And I argued that the best probability interval that you can quote, the highest posterior density interval, in this case is easy to calculate because it's the regular equally tailed interval that you will calculate anyway, okay, which is the mean plus minus a factor that depends on the probability that you want to the interval to have, and then scale by the standard deviation or the precision. Okay. One nice characteristic about Bayesian inference is that the approach is exactly the same regardless of the dimension of the problem, right? So, and that's what I want to illustrate with the extension of this example that we've also done before in the lectures. In this is the same example, so we have Gaussian data, but now we're assuming that we do not know the precision. So we need a prior on both parameters, and we prove that, hopefully you prove that, the conjugate prior is a normal gamma. That normal gamma is in your handouts, and that handout will be available in the exam, okay? So I would suggest that you use your handout as often as possible, because that will make the exam a bit easier for you, okay? So this is the prior that was elicited, and we know that this is a conjugate prior, so the posterior distribution is also a normal gamma with updated parameters, okay? So now we have a posterior distribution of dimension 2. And if we want to make inference, the only thing we need to do first is to marginalize the quantity of interest. In this case, the quantity of interest will be theta, the mean. And also in the lecture notes and in your handouts, you can see that if you have a normal gamma distribution, the marginal distribution of the mean is a student t with parameters that depend obviously on the parameters of the prior, and you have those relations in your handouts, so you don't need to learn them. And the marginal for the precision is a gamma with, again, the parameters depending on the updated parameters. And once we're here, we're back to the situation that we were before. We have a distribution on the parameter of interest. And if we want to do inference, we just need to use the corresponding loss function, right? The student, we know that is a symmetric distribution around its mean. And that means that the mode, the median, and the mean are the same. So that will be the base point estimate under any of those losses. The highest posterior interval, again, the distribution is symmetric, so it will be the equally tailed interval, which is constructed in exactly the same way, but now this factor comes from the t distribution, in this case with 10 degrees of freedom and probability 95. Okay? And if we want to test the hypothesis that the levels are safe, which means that theta is more than 16, we can again calculate that probability using, in this case, R. And in this case, we obtained 0.96, which is still larger than 0.9. So we can act as if the pollution levels were safe. Okay? So again, the mechanics are exactly the same regardless of the dimension of the problem. The only thing that we need to do is to find the corresponding marginal, okay, or the corresponding relevant distribution. And that is what we are going to try and do now with some more detail, okay? So we will work on example 562 on page 56. I will give you a few seconds to read through at least the first paragraph so you can familiarize yourself with it. Okay. So we have waiting times, hopefully, yeah. So we have waiting times on self-service checkout facility, and I believe that there are 3 checkouts apparently. Yeah. We have one queue that goes into 3 checkouts, and we have waiting times in that queue. Okay, and we're assuming that those waiting times are exponential with parameter lambda. Okay, so from handouts, we know that the PDF of each xi is that function over there, and we also have from the same handout the mean and the variance. Okay, again, this is assumed to be known because you have that in the handouts, and that will be in the exam. So now the unknown quantity here, the parameter is lambda. So we go to the manager who is interested in this problem and inquire about lambda in such a way that we can elicit the prior and we know now, hopefully, that a gamma prior is conjugate for the exponential model. So we will use a gamma prior. And I believe those are the values that were elicited. Okay? So to obtain the posterior, we need first the likelihood. And that is given that we are assuming that this is a random sample, it's a product over all the observations of each individual . So that's hopefully straightforward to everyone. And now the posterior distribution of lambda given the data, that is my lambda, is proportional to the prior times the likelihood. And that is proportional to lambda A minus 1, A minus B. And we know that this is, again, you have that in your handouts. This is the kernel, the most important part of the gamma distribution. So this has to be a gamma distribution in lambda with parameters A star and B star. And that is, again, from a Bayesian learning perspective, that is the end of the story. Okay? That's what we've done so far. We know how to do this. The new thing is how we do inference based on this. So if I want to calculate point estimates, the three options that we've studied are the point estimate under quadratic loss, linear loss, and 0-1 loss. Okay, under and again, I don't need to do anything to have this number because that's in my handouts. And that is A star or B star. Okay. Probably, yeah. On the 0-1 loss, I would need to calculate the mode of the distribution, right? And that is not in the handouts. So the mode is the value that maximizes the relevant distribution. So we need to find the value that maximizes, in this case, the posterior. Can you all see? Yeah? Cool. Probably you know this already, but it's usually easier if you want to find a mode, if you want to optimize a PDF or a likelihood, to first take logs and then take derivatives, right? And that's what I'm going to do. I'll shift this to the left. right? That is the log posterior distribution. If I take derivatives, then I can find the mode. The median would be the value that leaves half of the probability of, to either side of it. We cannot do that, at least not analytically, so we resort to R for doing that. Okay. So this is my, can you see, or is it way too small still? Is that any better? Not yet? Yeah, more or less? Okay. Cool. So you can download this script from the web page or mole, and this is just my attempt to try and illustrate what we're doing. That is data, some statistics, and those are the posterior values. Probably that will need to be also larger. Okay, so that is my A star and my B star. Point estimates. A star minus 1 over B star, that one there. If I want to find the median, I can use the quantile function in R, and the quantile of 1/2 is the median, so that is what I'm calculating here. And then I have A star over B star, which is the posterior mean. Okay? And I have them there. So you can see they're close to each other, but they are not the same. So just by quoting these three values, we already have some information about the shape of the posterior. Okay? It's more or less symmetric. It's not too skewed. And it seems to be more or less concentrated. Okay? But still, we can obviously plot it, and that's what I'm going to try and do. The next thing I would want to do if I carry on with my inference program is to calculate interval estimates. Okay? To calculate the equally tailed interval estimate, again, I would need to use R, and that would be easier in the sense that I would just need to calculate, again, the quantile of this posterior distribution that leaves 1 minus alpha to the left, and then the quantile of this same distribution that leaves 1 plus alpha over 2 to the left, right? To calculate the highest posterior density interval, that requires a bit more of maths. And this is my little function that calculates the HPD. Okay? What this means, practically for you at least, is that in the exam, if you are asked for an HPD, that means one of two things, and I will illustrate that in a second. Either that the posterior or the relevant distribution is symmetric, and therefore the HPD is the equally tailed, easy to calculate, or you will be able to actually integrate out or to integrate the posterior distribution or the relevant distribution, right? If you have a distribution of this type, I don't know where I wrote it, over like that, chances are that you won't be asked for an HPD, okay? Because that won't be, I was about to say fair, but it wouldn't be even feasible, okay? So I will calculate those here. Hopefully, yeah, there we go. So I have the equally tailed over there, and I have the HPD there. Probably doesn't say a lot. Probably one thing that is more or less clear from there is that the HPD is a bit shorter, and that's what we want. We want intervals that have the same probability content. Both of these intervals have probability 95. But the HPD is a bit shorter because it has, again, points that have higher mass. But probably what is more, it's easier to see is obviously the posterior distribution, okay? So hopefully that will give you an idea of what is going on. So the segmented lines are the equally tailed. So to the left of this line, it's 0.025 probability. To the right of this line is 0.025 probability. So in the middle, you have 95. And the red solid lines mark the HPD. As you can see, it's not equally tailed, but inside this interval, you have points in the posterior distribution that have higher density than any other value outside that interval, okay? So again, these are not extremely easy to find. They're also not too difficult, but they require a bit more of effort. Again, given that this distribution is skew, but it's not that skew, these two intervals are not too different. If the distribution was more symmetric, they will be more similar. If the distribution was more skew, they will be a bit different. Okay. So we've done all these. I was about to say for nothing, but it's that's not necessarily true. But we've done all these. But we need to take into account that the decision maker, the manager, is not interested in lambda. Lambda is a rate. What the decision maker is interested in is in the expected waiting time, because that is what she wants to advertise. She wants to know whether she needs to keep open the three outlets, the three machines, or she can close one. If this expected waiting time is smaller than, I believe, 3 minutes, probably. Okay, so what we need to do is actually make inference about 1 over lambda. Okay, so let's do that. And I think I call it psi there, phi. Right? So what we want to do is we want to make inference on the expected waiting time. So if I want to calculate point estimates, I would need to calculate the expected value of phi given the data, and this is the expected value of lambda to the minus 1 given the data. So that means that I can use, at least for this point estimate, I can use the posterior distribution of lambda to calculate that mean. Okay. Now, down a little bit. So here is where the integration in Bayesian statistics kicks in, because then we can write this down. As this factor that does not involve lambda, and then sorry, I'm dyslexic. So again, we can notice, and that's the reason why I'm writing this integral in this way, that this looks like a gamma distribution with parameters a star minus 1 and b star. So if I multiply and divide by the corresponding constant, this integral is 1 because this is a PDF. The first thing to notice is that the expected value of 1 over lambda is not 1 over the expected value of lambda, right? That will be a star over b star. So don't make that mistake, please. So far, or at least for the mean, we were able to use the posterior distribution of lambda to calculate that point estimate. However, if we want to calculate the mode, we will need the posterior distribution of psi. Okay? Because we need to optimize that distribution. So to get that, I need the Jacobian, and then I get pi of phi given x will be the PDF of lambda evaluated at lambda phi times the Jacobian, right? Well, the absolute value of the Jacobian. Instead of lambda, I have phi to the minus 1. Okay? And this is known as an inverted gamma distribution. With parameters A star and B star. Okay. Can you all see? Now I need to do the same thing I did there. Well, I will probably be easier to do this. I take the log and then take derivatives. So if I'm not wrong. Okay. Right? So now if we go back to R, I have the 3-point estimators there. We have B star over A star plus 1. Now, the median is, or any quantile for that matter, are invariant under monotonic transformations. So if I can calculate the median of lambda, the median of 1 over lambda is 1 over the median of lambda. It's just like the MLE. And then the mean over there. Okay. Now remember, we're interested in 3 minutes. That's the magic number here. And now these numbers probably make more sense, at least to the decision maker, right? We're talking now about waiting times or expected waiting times. And these are the 3 possible values that you can quote as point estimates, right? And now it's quite clear that the choice of the loss function will affect the final decision, right? The decision is to close the machine, I believe, if the waiting time is smaller than 3. If you're using only a point estimator, depending on which one you choose, you will make one decision or the other. Okay? I didn't bother to write in R the code for the HPD. I just calculated it in Mathematica, which is easier. But I'm plotting it here. And this is now the posterior distribution of the expected waiting times, right? Over there are marked the mode, the maximum value, the median, and the mean. And here we have the equally tailed and HPD intervals. Okay? This distribution is a bit more skewed than the distribution for lambda. So these 3 values are a bit more different. And also these 2 intervals are a bit more different. Okay? I have 5 minutes to. Okay. So I will walk you through these, and if you want me to, I can probably do some of the calculations on the board if in the next session, but I won't have time to do them all now. So I will just walk you through them. So the next thing that we can do is actually predict the waiting time of a client queuing at random, okay? Which probably is a better measure if you want to actually make a decision, right? You're not talking about expected waiting time based on the data. You are forecasting the waiting time of a future client taken at random, okay? So to do that, we just calculate the predictive distribution. I think you did a very similar exercise with Alison, didn't you? Hopefully, yeah? No? Okay. So I'll write it down. It doesn't seem that you did. So we're interested in the waiting time of a future customer. It's the same process, so that means that the distribution of that waiting time is the same distribution as those that we observed. So the predictive distribution will be the integral over of the parameter space, that's lambda. So infinity of f of y given lambda times the posterior distribution right? That's what we have there. And again, this looks like a gamma distribution, so I can use the fact that this will be a PDF with the correct constants added in. So I will do that. And doing some algebra, I can write that down as A star over B star